Hello everyone, my name is Manula Balasurya and in this presentation we will discuss our paper titled DaSSRNet Domain Adaptive and Semi-Supervised Signal Processing for Singing Voice Register Classification. This work was prepared for the 2026 22nd IEEE International Colloquium on Signal Processing and its Application or CSPA 2026. In the next few minutes, I will explain the problem the paper addressed, why that problem is difficult, the DaSSRNet method we propose, the dataset and evaluation protocol, the main experiment result, and the key conclusions. The main message of the talk is that single register classification is not only a classification problem. It is a classification problem under limited labels, domain mismatch, and substance acoustic boundaries between neighboring vocal registers. Let me first define the task clearly. The objective is to classify each singing frame into one of four vocal registers: vocal fry, chest or model voice, mixed voice, and falsetto. As summarized in the paper, chest voice is usually fuller and stronger in low to mid range. Falsetto is lighter and airier and often appears in high range. Mixed voice acts as a bridge between chest and falsetto, so it naturally overlaps with both. Vocal fry is an extreme low and creaky phonation pattern. This definition is important because the paper is not solving a trivial pitch sorting task. These classes have different timbral and psychological properties, and some of them, especially mix and falsetto, can overlap acoustically. That overlap is one reason for the classification problem is challenging. The paper addressed two linked difficulties in automatic singing register classification. The first is label scarcity. Expert register annotations are limited, expensive to obtain, and fragmented across datasets. Some corpora cover only a subset of the target registers, while others contain only short or narrowly defined clips. As a result, a model trained only on fully labeled data can overfit quickly. The second difficulty is domain shift. Different datasets vary in singers, language, style, recording conditions, and annotation conventions. A model trained on one source may therefore fail to generalize to another. There is also a third practical issue: pitch alone is not enough. Registers overlap in pitch range, and the same pitch can be produced with different vocal qualities. Therefore, the paper asks a focused research question: can weak supervision and domain invariant learning be combined to produce a register classifier that generalizes across multiple singing corpora? Our answer to that question is DaSSRNet, a two-stage framework. In the first stage, the model is pre-trained using pseudo-labeled data from vocal set. Since vocal set does not provide direct register annotations, the paper creates weak labels using technique tags together with pitch and spectrum-based heuristics. This stage gives the model a broad prior about how different registers tend to sound. In the second stage, the network is fine-tuned on curated labeled datasets, and domain-adversarial learning is activated to reduce dataset-specific bias. The model also includes an ordinal head that reflects the natural order of the target classes, from fry to chest to mix to falsetto. So, at a high level, DaSSRNet combines weak supervision for scale, supervised adaptation for correctness, and domain invariance for generalization. Now I will summarize the model architecture. The paper deliberately combines two complementary feature types. The first is a 96-band mel-spectrogram which captures timbral information and is processed by a convolutional branch. The second is a compact pitch feature vector derived from YAPT, including F0, delta F0, note, octave, voicing, and confidence, which is processed by an MLP branch. These two branches are fused into a shared embedding. From that shared representation, the model produced three outputs. The first is the main register classifier. The second is a domain classifier connected to a gradient reversal layer, which encourages the shared embedding to be less dataset specific. The third is a register height regressor, which imposes ordinal structure. This architecture reflects the paper's central insight that single register depend on both timbre and pitch, and that neighboring registers should be modeled as ordered rather than completely unrelated categories. The experimental design is one of the strong points of this paper. Pre-training uses pseudo-labeled vocal set frames. Fine-tuning and testing use three explicitly labeled sources: HFA fry for vocal fry, CC music for chest and falsetto, and GT singer for mix and falsetto. The paper performs a clip-level stratified split using 45% of the label clips for fine-tuning and holding out the remaining 55% for testing. This produces 150 fine-tuning clips and 186 unseen test clips, which correspond to about 19.2 thousand test frames. A validation subset is used for early stopping and temperature scaling. Importantly, the test portion is never used during pseudo-label generation or domain adaptation. That means the final evaluation is single disjoint and multi-corpus, so the reported numbers genuinely measure generalization to unseen materials. On the held out test set, the final model achieves about 0.79 frame level macro F1 and 0.79 frame level accuracy. At the clip level, performance improved further to about 0.87 macro F1 and 0.81 clip accuracy. This improvement is meaningful because a full clip is usually dominated by one register, even if a few individual frames near transitions are ambiguous. The paper also reports very strong performance on the extreme register vocal fry with approximately 98% precision and recall. The most difficult regions remain the boundary between mix and falsetto. In the summary table, the difference between the final model and the version without domain adaptation is modest. However, the paper emphasized that the much larger gain comes from the pseudo-labeled pre-training. Without that pre-training stage, frame level macro F1 falls sharply about 0.62. The confusion matrix helps us understand where the model succeeds and where it still struggles. Vocal fry is almost never confused with other classes, which is reasonable because its acoustic pattern is highly distinctive. The chest voice can sometimes be mistaken for falsetto, especially for high chest notes whose pitch and timbre approach head voice territory. The main confusion pair is mix and falsetto. This is also expected because these two registers form a continuum rather than a perfect sharp boundary. The paper then breaks performance down by dataset. HFA vocal fry clips achieves about 98% accuracy. CC music chest versus falsetto clip achieves about 76% overall accuracy. GT singer mix versus falsetto phrases are the hardest at around 69% accuracy. The paper further notes that domain adaptation improves GT singer mix versus falsetto discrimination by roughly 4% of points in F1, which supports the cross-corpus motivation of the method. The application study clarifies why the method works. The most important component is pseudo-labeled pre-training. When that stage is removed and the model is trained only on the small label set, performance drops from about 0.79 macro F1 to about 0.62. This indicates that the weak labels, although noisy, provide valuable prior structure. Removing domain adaptation causes only a small drop in headline metrics from 0.79 to 0.78, but the paper reports that it improves consistency across datasets. Removing the ordinal regression head decreases macro F1 by about 1.5 points and leads to less plausible mistakes. The box plots on the slide support this point. The predicted regression height values are ordered from fry through chest and mixed to falsetto. In other words, the model learns a meaningful continuous structure, not only four disconnected labels. To conclude, this paper presents DaSSRNet, a single register classification framework designed specifically for low label and cross dataset settings. The central problem is not simply assigning labels to frames. It is learning a classifier that remains reliable when expert labels are scarce and when training and test data came from different singing domains. DaSSRNet addressed that problem through pseudo-labeled pre-training, multi-source fine-tuning and domain-adversarial learning and ordinal modeling. The result shows strong overall performance and especially strong recognition of vocal fry, while also highlighting that mix versus falsetto remains the most difficult boundary. Future work identified in the paper includes adding more register labels, incorporating sequence modeling for temporal consistency, and exporting stronger domain adaptation strategies. Here are some of the references we have used in order to build this entire pipeline. And thank you very much for watching this presentation.